Hi. Now in this lecture we will be looking into the effect of substituents, right, on the acidity of phenols. When we say substituents, if we add a substituent, say a nitro group or a methyl group, right, in the benzene ring of phenol, then how will that gonna affect the acidity of phenol, right, or the resulting compound? For example, if I take this compound, right, NO2, now when we add it to water, it will form right and NO2 plus hydrogen ions. Now how this will affect the acidity, right, which what that means is, if we take just phenol, right, and add it to water, right, hydrogen ions. Now here this is phenol, right, and this is acidic because we have discussed this in previous lecture, because this phenoxide ion is more resonance stabilized compared to even phenol, right. So this makes the forward reaction to go, right, at a faster rate compared to the backward reaction, right. So this is more stable, right. That is why you have more hydrogen ion concentration in case of phenol, which will make it more acidic. And now if we add, say, nitro group, right, now how will this nitro group affect the acidity, right? Now when you add this nitro group, since the acidity depends on the stability of this ion, stability of phenoxide ion, right? Now this nitro group will increase this stability or decrease this stability, right? That's how it will affect the acidity of this resulting compound, right, which is orthonitrophenol, right. So we need to see whether the acidity of orthonitrophenol is more or less compared to phenol, right. Now mainly what we will be looking at, how the stability of this phenoxide ion, right, nitrophenoxide ion in this case, would be affected. Is it more or less compared to this, right, because on that only this hydrogen ion concentration depends. If it is less stable, it will combine with it to give you back the reverse reaction. So less hydrogen ion concentration means less acidic. If this is more stable, this is more stable, you have more hydrogen ions, more acidic, right. So let's see how the introduction of a substituent in benzene ring will affect the stability of this ion, right. So it depends on two things, right. How effect of substituents on acidity of phenols depends on two things. The first is nature of substituent. Nature of substituents. First would be whether it is electron withdrawing group, right, or it is electron releasing group, right. Electron withdrawing group is like NO2 group, Cl group, right. Electron releasing group is like methyl group, right, alkoxy group, right, or OH group, right. Now if you have electron withdrawing group, right, let's say you have electron withdrawing group, right, what it will do is, since this is an electron withdrawing group, NO2 is an electron withdrawing group, it will withdraw electron density from this benzene ring, right, making it less negative. Now when this is less negative, when this benzene ring is less negative, it is more stable, right, because if it is less negative, it has less chances of combining with this positive proton, which is hydrogen ion, due to which this compound is acidic, right. So if it is more stable, it has less chances of combining with this hydrogen ions, right. So less chances of combining with this hydrogen ion means you have more hydrogen ions. More hydrogen ions means more acidic, right. So electron withdrawing group will decrease the electron density of the benzene ring, making it less negative, right? Thereby increasing the stability. So electron withdrawing group will decrease the stability. Electron withdrawing group will decrease the electron withdrawing group will disperse the negative charge, to be correct. Disperse means it will lessen the negative charge. Disperse the negative charge, right? And thereby increasing the stability of, this is your ortho, say nitrophenoxide ion or nitrophenate ion, right? Now if you have, say, electron releasing group, right? Suppose in place of NO2 now I have this CH3. CH3 is electron releasing group, right? So what this electron releasing group will do, it will release electron towards benzene ring, right? Thereby increasing or intensifying the negative charge on the benzene ring, right? So when it is more negative, it has more chances of combining with this positive ion, giving you back this neutral compound phenol, right? Or giving you back, this not neutral, giving you back phenol, right? Which is unionized molecule, right? Because in this reaction only, this phenol is getting ionized to produce hydrogen ions, due to which this is acidic, right? So when you have this benzene ring is more negative, that means it will immediately combine with this hydrogen ions, giving you phenol, right? So what this electron releasing group is doing, methyl, it is intensifying the negative charge, thereby decreasing the stability, right? So it is increasing or intensifying negative charge on benzene ring, thereby decreasing the stability. Right? Thereby decreasing the stability. So presence of methyl group will, this ortho methyl nitrophenol, right? This is less acidic compared to phenol, right? And nitrophenol is more acidic compared to phenol, right? This is your cresol actually, right? So cresol is cresol is less acidic due to the presence of electron releasing group methyl group, and your nitrophenol is more acidic due to the presence of electron withdrawing group, right? Because this is what electron withdrawing and electron releasing group do. Now this is the first thing, nature of substituent. Now there is another point on which it depends, position of substituent. Position of substituent on benzene ring, whether the substituent, right, is present at ortho, meta or para, that will also affect the acidity. Right? Position of substituent on benzene ring. Right? So if the benzene, if you look at position, if the nitro group, right, in this case, I've drawn these structures to explain you this point. These are the resonance structures. We say that this ortho nitrophenol, right, and this para nitrophenol, right, these two are more acidic compared to metanitrophenol, right? So acidity of metanitrophenol is less compared to ortho and para. That means if the nitro group is present at meta position, the acidity is less, right? Whereas if it is present at ortho and para, then its acidity is more. And the other thing is, the ortho, if you compare between ortho and para, your ortho substituent, right, ortho is less acidic than para, right? So maximum acidity is of para, then comes ortho, then comes meta, right? Now let's look into the reason. What is the reason behind the variation of acidity based on the position of substituent on the benzene ring, right? Actually, we'll be looking into what is the difference when the substituent is present at meta position than when it is present at ortho or para position, right? So these are the structures of ion, right? Ortho nitrophenate ion, ortho meta or para. When this ortho meta or para nitrophenol is added to water, right? We'll be looking into the resonance structures in order to understand why meta nitrophenol is least acidic compared to ortho and para, right? So when you look at the resonance structures of this, when ortho nitrophenol is added to water, these are the resonance structures of this ion will result when this is added to water. This is your ortho nitrophenate, right? This is your para nitrophenate, right? And this is your meta nitrophenate. Right? One thing is clear, when we say that meta is less acidic, that means the electron withdrawing ability of meta is less due to something, right? And in these two cases it is more, because these two will be able to stabilize the nitrophenate ion to more extent compared to meta, right? So when you look at these two resonance forms, if you look at the resonance forms, just know how to draw these resonance forms, right? These are the 3 electron pairs on oxygen atom. The lone pair on oxygen atom will enter into resonance, right? Plus R effect with this benzene ring, right? This, due to resonance, this lone pair will enter into benzene ring, so we'll be drawing the different resonance forms, right? It will occupy the ortho meta para positions, right? So this electron pair is moving in this benzene ring. When it will reach here, you have a negative charge here. When it will reach at para, you have a negative charge here. Now when it will reach at ortho, you have a nitro group at ortho. This negative charge will move into this nitro group also, right? Thereby you have a negative charge on oxygen of the nitro group. If you look at this, you have a negative charge on oxygen of this nitro group, right? Similarly, if you look at para isomers, when this electron will delocalize into the benzene ring or move into the benzene ring, you have negative here, and when this electron pair will reach at para position here, it enters into this, it goes to this nitro group also, right? Thereby producing a negative charge. Now it moves back and goes to this ortho position, then finally to this, right? So this electron is moving from oxygen to back to oxygen, right, into complete this benzene ring, and it is entering into this nitro group also. So when it enters the nitro group, it's giving the oxygen of the nitro group negative charge. Here you have negative charge and here you have negative charge, right? So electron density is kind of dispersed on the nitro group also, right? But let's look at the meta, right? In case of meta, none of the nitro groups, right, none of the nitro groups has negative charge. That means electron is not, the electron, lone pair of electron that is moving is not entering the nitro group. It is not able to, the nitro group is not acquiring any negative charge because the lone pair is not moving into the nitro group, right? So its electron withdrawing group is kind of less compared to ortho and para, right? So you have no negative charge on any of the resonance forms of meta isomer, right? That is why this is less acidic compared to ortho and para, right? This is the reason why meta isomer is less acidic than ortho and para, right? I hope this point is clear, right? Just to revise again, out of the same number of resonant forms of ortho, meta and para. Ortho and para have, in ortho and para resonance forms, you have a negative charge on the nitro group, on one of the resonant forms of nitro group, right? This one, right? And in this case, in this one, right? Whereas there is no negative charge on the nitro group in case of meta isomer, right? So nitro group at ortho and para position is able to disperse the negative charge onto itself, right? Thereby decreasing the negative charge more, right? Lessening the negative charge more in the benzene ring, right? Thereby increasing the stability. More electron withdrawing means more increasing the stability of this ion, right? The ion, that nitrophenate ion that results when you add it to water, right? So more stability means more acidity, right? Basically. Whereas in case of meta, the electron pair could not enter this nitro group, right? Thereby its stability effect is less. It's able to attract the electron pair. It's not able to, the electron pair is not able to go to the nitro group, right? Therefore its withdrawing effect is less. Therefore it increases the stability to a lesser extent compared to ortho and para, right? This is the reason. Now if you compare the acidity between ortho and para isomer, right? Acidity, if this, in case of this ortho isomer, if you look at this, let's draw this ortho isomer. Right? You have highly electronegative oxygen and you have hydrogen here. So hydrogen bonding is possible, right? Because this nitro group is close to this OH, right? So you have, for a hydrogen bonding, we have a condition that you should have a highly electronegative oxygen and then hydrogen atom. So you can have hydrogen bonding here. So you have intramolecular, this is what? This is within the molecule. So we call it as intramolecular hydrogen bonding. Intramolecular hydrogen bonding. Now due to this intramolecular hydrogen bonding, release of this hydrogen ion, proton is difficult compared to in this para isomer, because in this para isomer, if you look at this para isomer, nitro group is far away from this phenol, so it could not make any sort of hydrogen bonding, intramolecular hydrogen bonding, that makes the release of this hydrogen ion difficult, right? So in this case, due to intramolecular hydrogen bonding, release of hydrogen ion is difficult. Release of hydrogen ion is difficult, that means it is less acidic, right? Because acidity is due to the release of this hydrogen ion, right? Now due to this hydrogen bonding, it is difficult for this hydrogen ion to get released, right? So this is less acidic compared to this para isomer, right? So maximum acidity is of para isomer. If we write it like that, maximum acidity is of para isomer, then comes your ortho isomer, right? Then comes your meta isomer. This is the order of acidity, right? I hope this is clear. This is important, right? Just understand the concept behind this, right? Whereas if you look at cresols, right, the effect of electron donating group is more pronounced at ortho and para position than at meta position, right? Same in case of cresols also, right? Since we know that, and here I just forget to mention that after this comes your phenol in this order, right? Now let's look at cresols. Cresol is when you have electron donating group, methyl group. Then how will it affect the acidity? Right? As we discussed earlier, that the presence of electron releasing group, that the group that releases electron into the benzene ring, will intensify the negative charge, and when it will intensify the negative charge, it will decrease the stability, because in that case that ion that has more negative charge will combine with hydrogen ion and will lessen the hydrogen ion. Less hydrogen ion means less acidity, right? So in that case, the order would be, since that lessens your acidity, so phenol will have maximum acidity. Let's just write it over here. Right, then comes your meta, right, because this would be more acidic, right, because this, what it is doing is it is releasing electron towards benzene ring, right, and the effect is less when the substituent is present at meta position, right, and when the substituent is present at ortho and para, when the substituent is present at ortho position, it is still less acidic. Right? Sorry, it should be para. The para should come first, right? Because we are going towards, it should be para first. Then your ortho will have, ortho is your least acidic. Right? This has maximum acidity. This is least acidic. Why this is least acidic among these two? Because this methyl group, right, can form hydrogen bonding with this oxygen atom, right? So whenever you have these two groups close, its effect is more. It's less acidic, generally, right? So I hope this order and this order is clear, right? Just understand how to write the resonance forms, right, and how does the electron withdrawing group and electron releasing group affect the ion, right? How does it affect the stability of your nitrophenate ion in these cases, and in these cases these cresol ions, right? I hope all this is clear. Thanks.